Let's start lecture 18 for the course corrosion protection methods, and today's topic we will be continuing our discussion on materials aspect for corrosion protection. So the course is and till now we have seen the effect of composition, as well as we started working on effect of microstructure. At least in case of stainless steel, we have seen that the chromium, if we increase the chromium content beyond 12%, as we increase chromium content, corrosion resistance of the steel improves. If we add molybdenum, we see that the pitting corrosion resistance improves. Again, if we reduce carbon content, we see that corrosion resistance improves. Like that way, we have also seen in case of microstructure that if the material is amorphous, that means there is no grain boundary, so then the material shows very good corrosion resistance. So that is what amorphous coating is an option for corrosion protection. And then we started discussing about grain effect. That means most of the cases our surface of the material reacting with the environment or the electrolyte will be polycrystalline in nature, and whenever we have polycrystals, it can be single phase or it can be multi-phase. Like let us say stainless steel, we have austenitic stainless steel. So that means all the grains are austenite, that means it is a FCC structure, but the grain size would be different. Similarly, in case of iron, commercially pure iron or commercially pure titanium, magnesium, mainly pure metal, where the phase will be single phase, but it can have a grain size ranging from nanometer to micrometer range. So that means fine grain and coarse grain, single phase as well as multi-phase. And multi-phase, when we go to alloy, then we experience multi-phase, but there also we can have difference in grain size of multiple phases that are forming in that material. And remember that whenever we have to see the microstructural effect on the corrosion tendency of the material, it is not like a straightforward that if we do fine grain, then corrosion resistance will improve, or if we do coarse grain, corrosion resistance will improve. There are several factors, and those factors will finally guide in combination, in totality, what will be the corrosion rate. So that is why it is very difficult to tell whether if we go straightway fine grain, it will show corrosion protection. So what are the factors that will decide the corrosion protection of a material if we consider only the microstructure part? Now, when we talk about microstructure, so that microstructure could be grain microstructure, at the same time surface stress can come in, and whenever we see microstructure, that microstructure can have different texture. Okay, so that way that the situation becomes very complicated. So that is what for different materials there is a kind of general observation that if we refine the grain, we see an improvement in the corrosion resistance, and in some other material, if we refine grain, we see that improvement is not there, rather corrosion rate increases. And there are some observations, scientific observations, that if we have this kind of situation, then we can have improvement in corrosion resistance. So we can talk on those scientific aspects, that when a material with different grain size or different microstructure can show an improvement in corrosion resistance. So, but we can list down some of the factors which are the guiding factors for the material to behave differently or in a particular way in a particular composition, particular solution. So, what are the factors? So, factors deciding corrosion rate, and we are talking about microstructure only. Now, we have already seen that the microstructure will have effect from composition as well as processing and as well as surface or bulk deformation. So, here surface and bulk deformation, we have to remember that even the bulk deformation would lead to change in the surface microstructure, as well as surface deformation would also lead to change in the surface microstructure. And since corrosion is a surface phenomena, so whether it is a bulk or surface, if there is an influence on the surface, it would definitely have an effect. So, that means these are the factors which will lead to some change in the microstructure, and here the microstructure we are talking about grain size distribution rather than no grain or amorphous. So, we have discussed amorphous part in our last lecture. So, let us talk about the grain structure. Or grain size rather, fine. And when we talk about the grain size, the factors if we talk about is distribution, size, texture, as well as there could be other effects which are coming not from the grain size. If we talk about other effects, so let us say these are in general some of the surface strain. Fine. So, these are some of the factors. Now, there is one more which is morphology, means it talks about distribution, size as well as shape. So, here I can put one more, shape, okay. So, that would give us the morphology, right. And texture is basically we are talking about microstructural texture. In fact, there could be surface texture which can be incorporated. Surface texture means the physical appearance of the surface, whether it is a smooth or angular. There could be a situation like if it is a pillared or if it is smooth, or if there are scratches in a particular dimension, particular direction, or there could be scratches in a kind of irregular fashion. All those factors will actually influence the corrosion of that particular material. So, for example, one particular structure could be smooth like this, there could be a structure like pillared, pillar, smooth, then scratch. So, if we talk about the surface, so it could be scratch could be in one direction, scratch could be in a particular pattern. Let us say this is the pattern scratch, there could be scratch could be irregular, okay. So, these are scratched surface. So, we are talking about the surface texture, the physical appearance of the surface, and its corrosion behavior can differ. Now, these are basically coming from the materials aspect. Now, we are actually having interaction of the material with the environment. So, this environmental factor also should be considered. So, now if we talk about environmental factor, so this comes under surface appearance, or we can say surface physical appearance. For example, general perception is smooth surface, better corrosion resistance. In fact, some of the corrosion forms that can be improved if we make smooth. For example, cavitation corrosion resistance would increase or would enhance. Because if it is smooth, definitely there will be difficulty in nucleation of bubble on top of it, and as we know that the cavitation is nothing but collapse of formation of bubble due to change in water pressure and then collapse of those bubbles giving shock waves on the surface, and gradually corrosion would go on. But mainly it is basically coming, this evolution is basically formation of bubble and then collapse of bubble leading to mechanical deformation on the surface, and that would also enhance the surface reactivity, and it would also increase the corrosion rate. So, there is another form which is, this is corrosion resistance improves if it is smooth surface. Then there could be forms like fretting. Fretting corrosion resistance also improves. Okay. Then we can also have better pitting resistance. So, these are the kind of situation we can end up experiencing. This is a general trend, I am talking about the general trend, but there could be a possibility that even if we have a kind of irregular or a kind of pattern on the surface, physical pattern like this pillared pattern, we can say smartly designed pattern. So, like pillared one, what it has been shown here. So, that can, if it would actually lead to hydrophobicity, it can actually improve corrosion resistance. Okay. Hydrophobicity, that means it does not attract water, and aqueous corrosion we have to have water. So, that then definitely it would improve corrosion resistance. So, these are general observation, but so that means scratch does not mean that it would always have a bad corrosion resistance or degraded corrosion resistance, but in general if it is smoothly designed pattern, then it can have hydrophobicity, it can improve the corrosion resistance, but in general if it is a scratch surface, then the corrosion resistance actually decreases. Okay. So, what are the corrosion pattern that can enhance corrosion pattern actually leading to enhanced corrosion? One is pitting corrosion, cavitation, fretting, even at times it can also lead to atmospheric corrosion. So, these are the general trends what we have observed, but finally we have to check what is the surface scratch pattern. Otherwise, if it is a scratch, definitely corrosion resistance would be negatively impacted. So, this is about the physical surface appearance. Then environment, this what we are talking about, these are general trend. Then we can think of solution, environment, effect. Different grain size, different medium, same composition can actually behave differently. So, we have some examples, we will try to show that. So, there is no general trend. Okay. So, now there are specific conditions when actually the material can actually improve its corrosion resistance depending on the microstructure as well as the surface appearance. Now, that means environment and solution or electrolyte or corrosive will be a factor, that means it can be detrimental to corrosion resistance or it can improve corrosion resistance. So, then that means if we see overall, we see that composition, grain size distribution, morphology, surface strain, like surface strain, if it is a compressive one, at times we actually get a very good corrosion resistance. For example, in case of reactive metals, so that the surface strain can actually improve corrosion resistance. In fact, if surface strain is compressive one, that means if we have short pinning kind of stuff, then in fact corrosion, stress corrosion resistance, even the corrosion fatigue resistance improves. So, that means there also this factor is playing a role. Now, if we look at this entire picture, so that means you can see that it is very difficult to draw a general trend that if we follow this route, we can have a very good corrosion resistance. So, that means depending on the materials, depending on the microstructure, depending on the distribution, we should be doing lab experiment to get an idea, and then we should follow up with the pilot plant trial if possible. Then we decide the choice of or decide the material for a particular application. So, now even it is very difficult, but there are some sort of scientific aspects. If the material follows those aspects, definitely we can actually design the route for or the protection method depending on the microstructure. So, like if we consider, for example, let us actually cite some examples. Now, if we talk about only grain size, let us take one example on single phase. Okay. So, there if it is fine and coarse, if we consider these two conditions, there could be different variations, like it could be a mixture of fine and coarse. The fine content could be large, coarse content could be large. Okay. So, those variations are possible, but if we only talk about fine and coarse, that means two extreme situation, and if it follows active behavior. Now, if it follows active behavior, then the fine grain material will show poor corrosion resistance. Now, what do we mean by active behavior? Material can show three different behavior when we polarize it in a particular electrolyte. So, it can show three behavior, and here active behavior we mean to say this one. Now, if we try to see the active behavior when we do dynamic polarization, then it can have a plot like this. This is log I, let us say ampere per centimeter square, because it is a log of current density, and this is the potential we are measuring in terms of volt. The schematically it would look like this. So, this is a typical active polarization behavior, and where this particular arm is anodic process, which is nothing but the metal dissolution process, and this particular arm is cathodic process, which is either hydrogen evolution or oxygen reduction or a reduction of oxidant. Other oxidant like ferric ion. Now, both this polarization are basically activation controlled, fine, and there is no signature of attaining passivity. So, that time the fine grained one would have higher corrosion rate. If we try to see it in this particular same diagram, let us say let us draw for the fine grained one, the fine grained one will show a plot like this. So, this is for fine grain, and this is for coarse grain. Fine. So, this is a general trend for a material when it shows active behavior. Now, why it happens like that? Now, there could be possibility of higher attack in case of fine grain. That is what this particular polarization line is moving towards right, and the corresponding corrosion rate, how do we measure? We just do a Tafel extrapolation, and this is my corrosion rate I core. Similarly, we do it for this case where Tafel extrapolation we are doing, and then we are finding this is I core for finer one. We could see there is a huge increase in corrosion rate if it is fine. Now, when we talk about coarse and fine grain, if the strain level is similar, so this is coarse one, this is fine one, okay. The only change is amount of grain size or amount of grain boundary if we talk about grain boundary area for fine grain, very large, coarse grain, small, if we talk about grain boundary area. Now, it has been observed that the grain boundary is the site for first attack, if we consider the corrosion attack. Since the fine grain has a large grain boundary area, so the attack points are also large, and that's what, and also they are not achieving passivity. So the amount of dissolution would definitely go up, and hence higher corrosion rate. And of course, here you will see improved corrosion resistance. But remember, that happens when the material shows active behavior all the time and they do not achieve passivity. So, we can add one more condition here. So, if we try to list down the two important factors, one is active behavior, and the second point we should see passivity is not achieved. So, that time definitely corrosion rate increases with finer grain size. Now, even if it is not activation control both the processes, but anodic process must be activation controlled, then only with finer grain size we have a higher corrosion rate. If it is, let us see that part. So, both are activation controlled. Another condition is coming up. Third is anodic process should be activation controlled. And no passive job. So, there could be possibility of concentration controlled cathodic process. Now, if we try to see that part, so there I can have anodic process as activation controlled, the cathodic process could be concentration controlled. I can, so here why it is concentration controlled? Gradually if we extend polarization, it will achieve limiting current density. So, there also fine grain would try to give a higher corrosion rate. Now, we have seen the logic that since the grain boundaries are attack sites, here the grain boundaries are attack sites. Let us see whether we have some proof for it. For that, I would like to show you one particular result from a literature. So, the literature is this one. In fact, this is one of our works. So, what we have done is we have tried to create a different grain size in a single composition steel. So, that means composition is fixed, but the grain size is changed. And how can you change the grain size? We deform the surface, and after deformation we try to do different degrees of annealing. and that annealing led to three different structures, rather 4 different structures. The as received, definitely it has a kind of uniform grain with little coarser grains like around below 30 micron grain size. Then we have created a grain size of 4 micrometer, we have created a grain size of 18 micrometer, and then we have tried to have a grain size distribution like fine grain and coarse grain. So, that means it is a bimodal structure. And of course, finally, we have also created a coarse grain structure with a single size grain size, single size grain. But since it is around 0.1% carbon steel, so that is what we can also see some of the pearlites in the material. Now, let us understand this typical experiment. If we see these particular images and let us see the experiments, what we have done, all those grain size materials steel actually we did dynamic polarization in 3.5% NaCl solution, and then after dynamic polarization, without doing anything, we took the sample and tried to observe the ACM micrograph, the surface pattern. And there we have observed for the as received one, which is around less than 30 micrometer grain. So, there we could see lot of pits, and if we follow those the cursor, you will see that wherever the cursor is moving or stopping, that basically part is the pits. And this is the as received one, which is uniform size grain of around 25 or around 25 to 28 micrometer grain. And then the second image, which is B, shows lot of pits, and here the grain size is 4 micrometer. And then if we look at the image C, which is also showing pits, but here the grain size has been increased to 18 micrometer, and the D is a mixture of fine and coarse grain. But as you see, from as received to 4 micrometer, since the grain size is becoming too fine, and of course we have lot of pits, that means it gives an indication that since the grain boundary area is increasing, we are having lot of pits here, and you can visually see that the pit number has increased greatly. But once we convert this 4 micrometer to 18 micrometer grain material, we are seeing the pits are forming, but the number of pits has reduced. But if you compare with the as received one, the number of pits in case of 18 micrometer, which is the C image, is larger than the as received one. But once we go to a bimodal structure, which is fine and coarse grain, we could see the pits are there, but still we could see that the number density of pit has reduced compared to 18 micrometer grain size material. So, that means it gives an indication that if we go to fine grain, we can increase the number of pits, and it also indicates that since their only change that is brought up is basically the grain size or the grain boundary area has increased. Of course, there will be little strain here also, because if it is 4 micrometer strain, it's the strain is not completely relieved, but still majority effect is coming due to the grain boundary area enhancement. Now, we have to see whether the attack is actually happening at the grain boundary. So, for that what we did, we have taken a coarse grain material for this, which is the grain size is around 34 to 35 micrometer. So, there what we have seen that this is the surface we are talking about now. Now, we could see some of the pearlites. If you see this cursor, these are the pearlite. These are the pearlite, and of course, you will find pearlite in case of 0.1% carbon steel, which is definitely mild steel, and there, as per the phase diagram, the steel part of iron carbon diagram, we can calculate what could be the amount of pearlite there. So, it will be a mixture of pearlite and ferrite grains, and we will also have interface between pearlite colony and ferrite grain. Now, this material initially it showed pits, but much lesser pit, and it did not show any signature of any features of grain, but here you could see that initially when we have taken it from the after doing polarization. Now, if we polish the top surface, that is a light polish on a cloth, and then take it to SEM, in fact you will start seeing the grains feature. So, these grain features you can obtain by etching, and when you do etching in NPTEL, clearly you can see those grains and pearlite, but here etching was not used. Just after polarization we have taken it to the SEM. So, that means it must have got etched due to electrochemical process during polarization. So, there we could see a nice grain pattern as well as pearlite. And now we have also observed some interesting features. Here we also see pits. So, this is one pit, this is another pit, this is another small pit, this is another pit. So, wherever my cursor is moving, you just follow that cursor, you will see those pits have actually coalesce, and then it is forming a kind of a deep line along the grain boundaries, and everywhere you could see, for example, here if you see this part, here also it is showing those pit patterns are actually combined, and then it is forming a kind of a groove. So, these are actually forming along the ferrite grains interface, that means grain boundary, ferrite grain boundary, whereas if you consider this particular, you follow the cursor, here it is falling at the pearlite ferrite interface. So, that means pearlite colony and ferrite grain interface that is forming. For example, here the 3 pits. So, 3 pits are actually along the ferrite grain. So, that means every time we are seeing some of the pits, they are actually forming along the grain boundaries, whether it is an interface between pearlite colony and ferrite grain or between ferrite and ferrite grain. And it also gives a clear indication that the first attack sites are basically nothing but the grain boundary or the interfaces. Now, question is, why do you say that this is first attack site? Because initially we could see pits on the surface, and there these grain features are not reflecting, but once we polish it little bit, so that means we are removing the top surface and we are actually exposing the subsurface, and there we can definitely see some features which have happened in the beginning of the polarization process. So, that is what we can surely say, that those particular pits are forming in the beginning or beginning of the process along the grain boundary. So, similarly for the fine grain the same observation can be noticed. So, it clearly reflects that grain boundary sites are basically the attack sites, initial attack sites. Now, question is what we have observed in that paper. So, what we have observed, that these particular material in 3.5% NaCl solution did not show any passivity. So, it showed all the time active behavior, and some of the cases we saw both cathodic and anodic process are activation controlled, and in some cases we saw that anodic process is definitely activation controlled, but the cathodic process could be concentration controlled. So, that means both are possible, but it does not show any passivation, and that is what we have also seen, that the 4 micrometer grain size material has the highest corrosion rate, as well as we increase the grain size, we could see that the resistance to corrosion in 3.5% solution also has gone up. So, this particular result clearly shows that if we have fine grain and if the material shows no passivity, only active behavior, then the material would experience poor corrosion resistance if it is finer. Okay. So, that actually has been explained here. So, now we have explained only the active part. We will discuss this active passive and spontaneous passive material, a spontaneous passive case, these two cases corresponding to fine and coarse grain in our next lecture. But at least this is a general trend again, as we have indicated in case of surface features, that fine grain would show poor corrosion resistance if it follows active behavior as well as passivity, no passivity situation. Whether the arms are, that means cathodic and anodic arms are activation controlled. So, that means cathodic arm is activation control or concentration control, anodic process must be activation controlled. Okay. So, that case this is a general trend. So, again I should write here, this is a general trend. In case of mild steel, it is a highly possible option. But remember, as we are indicating that we have to find a trade off, that in order to get a better corrosion resistance in terms of grain size, we must not make it coarser, because if we make it coarser, we are actually losing the toughness. As we know, finer material shows a better toughness, and for that we know the Hall-Page equation is active. So, Hall-Page equation which shows the flow stress is proportional to grain diameter, inversely proportional to the grain, half of grain diameter. So, D is basically grain size in terms of diameter. So, there we always, most of the cases we try to make the material finer to get an advantage of higher toughness. So, now if we consider this corrosion as well as toughness, it is a trade off between these two. So, let me stop here, we will continue our discussion on the effect of grain size in our next lecture. Thank you.